Hello everyone, I'm Rajendra, currently a second year MSc Math student at IIT Bombay. Last year, while being at IIT, I had the chance to participate in Simon Maria's Mathematics Competition 2024. In the paper B of it, there was a combinatorial search problem which I was not able to solve in exam time. In the problem, there are two kids, Alice and Bob, and they are playing a game. Alice has six boxes labeled through 1 to 6. She secretly chooses exactly two of the boxes and places a coin inside each. And then Bob is trying to guess which two boxes contains the coins. Each time Bob guesses, he does so by tapping exactly two of the boxes. Alice then responds by telling him the total number of coins inside the two boxes that he tapped. Bob successfully finds the two coins when Alice responds with the number 2. The problem is to find the smallest positive integer n such that Bob can always find the two coins in at most n guesses. Alright, let's start with the fundamental question why such a smallest n should even exist. Well, basic combinatorics tell us that there are only 6 choose 2, that is 15 distinct guesses Bob can make. And because coin remains in the same boxes even after Bob make a guess, so Bob don't have to repeat the same guess. Thus he can always find the two coins in at most 15 guesses. So the smallest number will exist. Suppose n is the smallest number of guesses needed to find the two coins always. So n have to be less equals to 15. Now the question is, can we do better? And the answer is yes, we can. We can bring down the upper bound to 5. Suppose Bob's first guess is box 1 and box 2. Now he can fix one of the boxes. Suppose he fixes 1 and can choose his second guess to be box 1 and box 3 and his third guess to be box 1 and box 4 and his fourth guess to be box 1 and box 5. Now, if any of these gets a response of 2, then Bob has already found the coins. Otherwise, at least one guess must have received a response of 1. If there was exactly one response of 1, say for the guess box 1 and box K, then box K and box 6 will be the fifth winning guess. If there were exactly two responses of 1, say for the guesses box 1 and box M and box 1 and box K, then box M and box K will be the fifth winning guess. If there were more than two responses of 1, then box 1 and box 6 will be the fifth winning guess. Observe that it does not really matter what Bob's first guess is. He can always follow this strategy to find the two coins in at most 5 guesses. Thus, n is less equals to 5. Now the question is, can we do even better? And this time the answer is a big no. 5 is the optimal value, but we don't need a proof for that. And for a proof, first we generalize the problem in the following way. As there are 6 boxes in the original problem, we can call it a 6-box game and generalize it to a m-box game for any natural number m greater than equals to 2. And now we define n of m to be the smallest natural number such that Bob can always find the two coins in a m-box game in at most n of m guesses. Now a question arises, why does this generalization even helpful? And it's helpful because firstly, it is easy to determine n of m for small values of m as there are not much strategies possible for small m. Secondly, our original problem is to find n of 6. And lastly, we can recursively find n of m using first few values. First, observe that for m equals to 2, there are two boxes with a coin in each. So there is only one possible guess. So n of 2 is 1. For m equals to 3, without loss of generality, assume that Bob's first guess is box 1 and box 2. Because out of 3 boxes, 2 have a coin. So Alice's response to this guess can either be a 1 or 2. If it's 2, Bob won in just one guess. If it's 1, then Bob have to make his second guess. But now he knows that third box have a coin. So as he doesn't know other coin is in which box, So box 1 and box 3 and box 2 and box 3 are equally probable guesses, and hence he needed at most two more guesses to find the other coins. So n of 3 is 3. For m equals to 4, without loss of generality, say the first guess is box 1 and box 2. If the response is 2, then the game is won. And if the response is 0, then the second winning guess would be box 3 and box 4. Otherwise, the response is 1, in which case, guessing box 3 and box 4 as next guess will provide no information, as we already know the response is going to be 1. Now we are at a stage where we have two pair of boxes and each pair have a coin. So the second guess must include one box from box 1 and box 2 and one box from box 3 and box 4, which without loss of generality can be assumed to be box 1 and box 3. Again, if the response is 2, then done. If it's 0, then the third winning guess would be box 2 and box 4. Otherwise, the response is 1. Now, depending on the fact that either box 1 has a coin or not, the winning guess is either box 1 and box 4 or box 2 and box 3. As we don't really know box 1 contains a coin or not, in the worst case, at most two more guesses are required. Thus, 4 guesses are enough always, and exactly 4 are required in the worst case. So, n of 4 is 4. Now we establish an inequality between n of m and n of m minus 2 for m greater than or equals to 4. Suppose we are solving a m box game and our response to the first guess happens to be a 0. Then it means both the coins are in remaining m minus 2 boxes. So after the first guess, the problem is equivalent to a m minus 2 box game. Thus, in the case when the first guess gets a response of 0, we need at most 1 plus n of m minus 2 guesses. So we get that n of m is greater than or equals to 1 plus n of m minus 2 for m greater than or equals to 4. Now using this inequality for m equals to 6, we have that 1 plus n of 4 is less equals to n of 6, and which gives that n of 6 have to be at least 5. But we already proved that n of 6 is at most 5. So we conclude that n of 6 is 5, which solves our original problem. Now the question is, can we go a bit further and solve for n of m for any value of m? At first it looks extremely difficult, but it turns out that there is a nice formula for n of m. To establish that, first we put an upper bound on n of m. We make two cases because the strategy is going to be different for even and odd values of m. When m is even, say m is 2k, we use the following strategy. We first choose box 1 and box 2 as the first guess, box 3 and box 4 as the second guess, and so on till box 2k minus 3 and box 2k minus 2 as k minus 1 guess. If they all have a response 0, then kth winning guess would be box 2k minus 1 and box 2k. If any of them gets a response of 2, we won in at most k minus 1 guesses. Otherwise, one guess must have got a response of 1. If there is exactly a single response of 1 in the first k minus 1 guesses, then we know that the response of box 2k minus 1 and box 2k is 1 as well. Thus, in at most k minus 1 guesses, we are at a stage where we have two pair of boxes and each pair have a coin. Now we just need at most 3 more guesses to find the coins, as we did in the case of m is equals to 4 at some point. Thus, k plus 2 guesses are always sufficient to find the coins. So n of m will be less equals to k plus 2. That is, n of m will be less equals to m by 2 plus 2. Now we move to the second case when m is odd. Say m is 2k plus 1. Firstly, we choose box 1 and box 2 as the first guess, box 3 and box 4 as the second guess, and so on till box 2k minus 3 and box 2k minus 2 as the k minus 1th guess. If we got a response of 2, then we are done in just k minus 1 guesses. If all of these guesses have a response 0, then it boils down to a 3 box game, and which requires at most 3 guesses. Thus, we are done in k plus 2 guesses. If there are 2 responses of 1, then at most 3 more guesses are required. Thus, still at most k plus 2 guesses are sufficient. If we got exactly single response of 1 in these k minus 1 guesses, say box 1 and box 2 get a response of 1, then we choose box 1 and box 2k minus 1 as kth guess. If it's a 2, then done in k guesses. If it's a 0, then we can guess box 2 and box 2k, and box 2 and box 2k plus 1 in turn, and win in at most 2 more guesses, and hence done in k plus 2 guesses again. If box 1 and box 2k minus 1 gets a response of 1, then we choose box 1 and box 2k as k plus 1th guess. If its response is a 0, then box 2, box 2k minus 1 is the k plus 2th winning guess. If it's a 2, then we are done in k plus 1 guesses. If it's a 1, then we must have a coin in box 1. Otherwise, it forces to have a coin in each box 2, box 2k minus 1 and box 2k, which means we have more than 2 coins, which is not true. Now observe that the other coin is in box 2k plus 1, so we can make our k plus 2th guess to be box 1 and box 2k plus 1. Thus, k plus 2 guesses are always sufficient to find the coins. So n of m have to be less equals to k plus 2 again. That is, n of m have to be less equals to m plus 3 by 2 in the case when m is odd. Now these upper bounds along with the inequality 1 plus n of m minus 2 less equals to n of m can be used together with strong induction to prove that n of m is given by this nice formula. The proof via induction is easy. I leave it to you. Thanks for watching.